All right, now what I'd like to talk about is the concept of electroosmotic pumping, a mechanism that exploits the charge double layer and the charge imbalance that exists in it to force the mobile charges down a channel. So as we've talked about, any solid wall will have some amount of charge buildup on the side walls. Depending on what the chemistry is, that could be positive or negative, but there'll always be some kind of charge buildup on the walls of a channel. And if you have an ionized fluid that fills the space between that channel, you'll get a charge double layer that builds up near the wall within one so-called Debye screening length. Typically a couple of nanometers in size, but it can be larger depending on the fluid and how the charge density is set up in the fluid. So the idea behind electroosmotic pumping is that we'll apply electric field along the channel, and that will force the charge that's in the double layer towards the direction of the electric field. So let me write out the Navier-Stokes equation inside the entire fluid channel. I'm going to assume that there's fully developed flow here. In that case, mu, the viscosity, times the second derivative of the velocity along the y direction will be balanced by the forcing function, which is the net charge density times the electric field. And of course, the net charge density here is only non-zero inside the charge double layer. So we're going to apply this electric field. We can turn that net charge, so that net charge, because we can relate that using Gauss's law to be related to the electrostatic potential inside the double layer, as we've shown in the double layer series of lectures. And then what I'll do is I'll go about like solving that Navier-Stokes equation. So so outside the double layer, that's actually incredibly easy, right? Because the net charge density is zero outside the double layer, which means that there is no forcing outside the double layer. So that electrostatic potential term is zero. So in that case, you can just directly integrate the Navier-Stokes equation once and then twice. And you find out that at most there can be a linear velocity profile, but by symmetry we know that it's not actually linear, right? It has to be a symmetric function. And so we know that the term associated with C1 is zero by symmetry. And the only thing that it could possibly be is that, at least outside the double layer, the solution is that the velocity profile is just a constant. So let me call that constant U0, which is just the velocity. So there's just some constant velocity outside the double layer. And then let's figure out what's going on inside the double layer. Okay, so if I rewrite the Navier-Stokes equation inside the electric double layer, then I will have a forcing term. So I'll still have I'll still be able to integrate it one time because they both involve second derivatives. That'll produce an unknown, what I'll call C2, after integrating one time. And then I can try and apply a boundary condition somewhere, right? Well, one of the easiest boundary conditions that I can think of applying would be at the edge of the charge double layer. So kind of outside the double layer, but I would think about it more like at the edge of the charge double layer on the interior of the channel. I mean, at that point, the two solutions need to merge in some way. And so we know that the electrostatic potential should converge towards zero on the inside, or the slope should even out. And similarly, we know that inside the charge double layer, the velocity profile is a constant. So that means that both of the slopes of like the velocity and the potential are zero inside the charge double layer, which means that C2, that the unknown constant of integration, also has to be zero. From there, we can just integrate one more time. I'll do a definite integral because it's a little bit easier. I'm not really sure what terminology to use here, but I'm going to integrate from one edge of the double layer to the other side. So from the wall to the interior. At the wall, I know that the velocity itself is 0 by the no slip condition, and inside or outside the electric charge double layer, I know that the velocity is u0 from above. I can do the same thing, do the same integration inside for the potential, and what I'll find is that the potential inside the charge double layer is 0, which leaves only the so-called zeta potential left on the inside. So let's put all that stuff together. So after doing the integration and eliminating some constants of integration, what I can do is I can identify the fact that mu times u0 equals the permittivity times the zeta potential times the electric field. In other words, I can identify, or I can solve for the velocity profile inside the charge double layer, or sorry, in the region that's not in the charge double layer as a function of the applied electric field. And I'll find out that that thing is essentially just proportional to the zeta potential, which represents the charge, and is inversely proportional to the viscosity of the fluid.